So this section is really a continuation of section 4.2. I'm not really sure why I pushed this to the back of the chapter as opposed to just extending section 4.2, but it is what it is. So in section 4.2, we talked about the counting principle, and the counting principle involved experiments. Very specifically, the counting principle said if two experiments were performed, if a first experiment could be performed m distinct ways, and a second experiment could be performed n distinct ways, then those two experiments in order can be found. The number of ways those two experiments can be done in order can be found by multiplying the number of ways each experiment can be performed. So if the first experiment could be performed m distinct ways, and the second experiment can be performed n distinct ways, then the counting principle said there's going to be m times n ways those experiments can be performed in that order. So we're just going to do fancier, more complex counting principle problems, but not like the most complex counting principle problems ever. I actually took a class in grad school where we worked on some bizarrely hard counting principle problems that didn't sound that hard when you read through the problem, but boy, they were really hard to figure out how to set these things up. So let me just do some examples with you before we jump into the problems. So here's a counting principle problem. A computer password is to consist of 2 lowercase letters followed by 4 digits. Determine how many passwords are possible if, and then we'll get to the if here in a second. So essentially, the experiments I'm doing, I'm going to pick, experiment 1 is going to be to pick a first letter. That's my first of, I guess, 6 experiments. My experiment 2 is going to be to pick a second letter. And then experiments 3 through 6 are going to be picking numbers. So a first number, a second number, third number, and a fourth number. And back in section 4.2, we learned that you could extend the counting principle to more than 2 experiments. And this is an example of using the counting principle to figure out how many passwords are possible when there's kind of 6 different experiments being done. It's kind of strange to call this experiment, but this is what we need to call it. So, case 1, if repetition of letters and digits is permitted. So, in order to do this, I need to know that the alphabet has 26 letters and that there are 10 digits. The letters I'm not going to write down, but the digits are the numbers starting at 0 and ending at 9. So the numbers 1 through 9 give me 10 digits, and then adding the 0 gives the 10th digit. When repetition is allowed, this is like with replacement, meaning if I use a letter once, I'm allowed to use it again, or if I use a number once, I'm allowed to use it again. And essentially, for each one of these choices, I just need to put the number of letters or the number of numbers that are available for that slot. For the first letter, I can use any of the 26 letters in the alphabet. And because it says repetition of letters is permitted, that means I'm allowed to, whatever letter I chose for the first letter, I'm allowed to use it again. So the second letter is also going to have 26 letters to choose from. Each of the numbers, because I'm also allowed to repeat digits, is going to have 10 choices, because each time I'm allowed to use any of the 10 numbers between 0 and 9. This is the setup to figure out how many passwords are possible having 2 lowercase letters followed by 4 digits. I'm sure I did exactly this as I go through my work. And stumble on to the next page, I find I just have to multiply those numbers together to get the number of passwords. Let me just do that real quickly by going 26 times 26 times 10 times 10 times 10 times 10, and that gives me 6,760,000 passwords are possible if the form is 2 lowercase letters followed by 4 digits, and I'm allowed to repeat letters and repeat digits. When I move on to a part B, we're going to find out how many of these computer passwords are possible if repetition of letters and digits is not permitted, meaning once I use a letter, I'm not allowed to use it again. And this is kind of, if we want to go back to the section 4.2, this is like a without replacement problem. So when repetition is not permitted, I think of this as without replacement, and I'm going to have to increment down one each time that I use up a letter or a number. So my 6 experiments are getting a first letter. I'll just say letter 1, letter 2, and then number 1, number 2, number 3, and number 4. I have the same 6 experiments, but I'm not going to get the same numbers in each of the slots. For the first letter, I have all 26 letters in the alphabet to choose from. But for the second letter, because once I take a letter out, I'm not allowed to use it again. I'm not going to put it back and make it usable. For the second letter, I'm only going to have 25 letters to choose from. The numbers are going to work the same way, or the digits are going to work the same way. The first digit has all 10 digits to choose from, the numbers 0 and then 1 through 9. And then, because I'm not allowed to repeat a digit, whatever digit I used on the first one, it can't be used for the second one. So if I use 3 for the first one, it can't be used for the second digit, and I'm only going to have 9 digits to choose from for the next third digit. After I pick 2 numbers, whichever numbers they are, there's only going to be 8 numbers left for the third, and then 4 numbers for the last. So I just need to increment down 1 each time. Apparently, if I do this multiplication and I haven't made a mistake, if I pulled out my calculator and did 26 times 25 times 10 times 9 times 8 times 7, I'd get 3,276,000 passwords, which is a lot less than the 6,760,000, almost half, in fact, just about half as many passwords, because you're throwing out a lot of passwords here. Any password that had a double A or 2 7s in it would be thrown out in this instance. Let me do another example, just so we can kind of get used to just some of the terminology that's going to come up in this section. So we're doing the same style of problem. I'm finding how many computer passwords are possible that have the form 2 lowercase letters followed by 4 digits. And I'm considering these 6 separate experiments. Each time I pick a letter, it's considered a separate experiment. Each time I pick a digit, it's considered a separate experiment. So for each part of this, I'm doing the same setup. But now it gets crazy. So the first thing it says, the first letter must be a vowel, A, E, I, O, or U. So for the first letter, the choices I have are A, E, I, O, and U. I'm assuming Y is not a vowel. And for the first letter, because it must be a vowel, I'm going to put a 5 above it, because there's 5 ways that experiment can be performed successfully. And then, still talking about the letters, it says repetition of letters is not permitted, meaning once I use a letter up, I'm not allowed to use it again. Usually, there's 26 letters in the alphabet, but I placed one of those 26 letters, and I don't know if I placed A, E, I, O, and U, but whatever letter I placed here, because repetition of letters is not permitted, I have to lose the letter that I placed first and there's going to be 25 letters to choose from for the second letter. Ugh. Now down to the numbers. So done with the letters, down to the numbers. The first digit can't be a 0, which means the first digit can only be the numbers 1 through 9. So there's only 9 choices for the first digit because it can't be a 0. Now it says repetition of digits is not permitted. So for the second digit, there normally would be 10 digits to choose from, but I picked one of the numbers. I don't know which number I picked. I picked one of the numbers, so I need to lose the one that I picked. I can't pick it again. The second digit is going to be 9. For the third digit, there's 10 digits normally, but I have 2 digits placed already, so I'm going to put the 8 choices I have for the third digit. And for the fourth digit, there's 10 digits normally, but I've placed 1, 2, 3 of them. There's only going to be 7 choices for my fourth digit. If I want to find out the number of computer passwords of this style that are possible, I'm going to go 5 times 25 times 9 times 9 times 8 times 7, and I'm going to get 567,000 passwords of the form a vowel, and then a letter, and then a number between 1 and 9, and then 3 more digits when you can't repeat letters and you can't repeat digits. So these things can get really hard really quickly. We just have to take them as slow as we can, just kind of work our way from left to right, and just trying to logically think about the number of choices we have for each option. All right, done with the license plate samples, but our password samples, but we're certainly going to get more of those once we get to the homework. So another example, Bob, I wish I didn't have 2 people with the same names, the same letter. Bob, Sue, Larry, so I'll go Sue, Sally, and Fred are waiting in line to buy concert tickets. So there's 5 people waiting in line to buy concert tickets. And this says, in how many different ways can they stand in line? Well, my experiment is lining these people up. And there's 5 experiments that I'm doing here. So I'm going to make 5 dashes. The first experiment is going to be selecting the person that's first in line. Then I'm going to select the person that's second, third, fourth, and fifth in line. You notice in the wording, I didn't say anything about with repetition or with or without replacement. It's because it's implied by the problem. So for the first person, any one of the 5s, Bob, Sue, Larry, Sally, or Fred, could line up first. There's going to be 5 people that could line up first. But there aren't going to be 5 people that can line up second. Let's just pretend Sue is first. If Sue is first, she's already placed in line. She can't line up second, third, fourth, or fifth. So once I pick somebody to line up first, I only have the other 4 people that are available for the second slot. So this is like a without repetition, without saying without repetition. So let's say that Larry was second and Sue was first. Well, then for the third person, there's only the 3 people that aren't lined up yet. And I have to increment down by 1 for each of the remaining choices. So, and in most of these problems, either the numbers are going to remain the same, or they're going to increment down by 1. Of course, we have the vowel kind of variation on these problems. But for the most part, as we're going to place numbers above the lines for each of the experiments, I'm going to have to decide if it doesn't tell me repetition is allowed or repetition isn't allowed, if it makes sense to keep the same number or if I have to increment down. Here, it didn't make sense to keep 5, 5, 5, 5, 5 because the same Sue couldn't be first, second, third, fourth, and fifth. She could only be in one of those spots. And I believe if we multiply this 6, I think this comes out to 120. So there's 120 different ways these 5 people could stand in line. Here's a variation that's not so nice. So how many ways can they line up again? So we had Bob, Sue, Larry, Sally, and Fred. And those 5 are going to line up in line to get concert tickets. Tell this is an old question because we all buy our concert tickets online now. We almost never line up. But boy, when I was in the 80s, we'd fight for that first spot in line because you can get good tickets, and they didn't used to charge extra to sit in the front row in the 80s like they do now. So anyways, how many ways can they line up if Larry insists on being in the middle? Well, I believe this is the middle spot right here. And it says Larry's got to sit in that middle. So I'm going to deal with this first. If Larry insists on being in the middle for whatever reason, just because I wanted to make a cute problem, I guess, there's only going to be one choice for the middle person, and it has to be Larry. So I've got Larry standing in line, and now I'm going to fill in the other persons, the first person, the second person in line, Larry's third, the fourth person, and the fifth person. And there aren't any other restrictions. So to line up first, any other one of the 4 people that aren't in the middle can be first. Say Sally was first this time. And then if Sally was first and Larry's in the middle, then Bob, Sue, or Fred can be second. And there were 3 choices there, Bob, Sue, and Fred. And let's say Fred happened to be second. Then for the 4th and the 5th, there's just Bob and Sue left. So there's 2 left there. Say Bob was second. And then last, there'd be 1 for Sue. So I increment it down again because the same person couldn't stand in 2 places. But I dealt with Larry first because he had a specific spot to deal with. If I multiply these numbers together, there's going to be 24 ways these people can line up if the Larry has to stand in the middle. Alright, how about if Sue insists on being first and Bob being last? So again, the people were Bob, Sue, Larry, Sally, and Fred. So I'm going to line up these 5 people, so I'm doing 5 experiments. So there's a first person, second, third, fourth, and a 5th. And it says if Sue insists on being first, Bob has to be last. How many ways can they line up? So for the first person, it has to be Sue. For the last person, it has to be Bob. So there's only one choice for the first person. It's specific, it only could be Sue. There's only one choice for the last person. It can only be Bob. So I've just placed Bob and Sue where they have to be. There's only one choice for the first person, one choice for the last person. Now for second, third, and fourth, any one of Larry, Sally, or Fred could be second, third, or fourth. So there's 3 people that are left for that position, and it doesn't matter who got second. Let's say Fred got second. Well, then for the third position, there's only going to be 2 left. And whichever one of these 2 came in third, there's only going to be one choice for the fourth person. So now there's really very few options. There's going to be 6 ways. If Sue insists on being first and Bob has to be last, there are 6 ways that these 5 people can line up. So if we snuck a peek at the title of this section, if I could even find the title of this section anymore, I'm not so sure I can. No, apparently I can't. Oh well, really. So this section was called the counting principle and permutations. The counting principle is what we've been using to figure out how many ways we can generate computer passwords or how many ways people could stand in a line. A permutation is a very special subset of the counting principle. It's a special kind of counting principle problem. And there is an alternate way to answer some of these questions if they're a very specialized problem. specifically, a problem is a permutation problem if all the objects that we're ordering are from one set and repetition isn't allowed. So all objects from the same set repetition not allowed. And the very first problem I did with Bob and Sally and Sue and Fred and Larry was the classic permutation problem. We had 5 people from the same group of people from the same set that were lining up, and they weren't allowed to line up in the same space. I could have solved that problem differently, but it would have been way more complicated, and it's something that I'm not going to discuss. If you were a math major, I'd talk about these special kinds of counting principle problems and make a big deal out of them, but boy, they're not a big deal. And every problem in this section can be solved using the counting principle, making little dashes and putting numbers in those dashes. And it kind of overcomplicates it if we start talking about this special kind of problem that maybe for every 10th problem you could use a special way to get the answer to the question. It kind of just muddies the water. So we're not going to worry about permutations at all, although a permutation is a special kind of counting principle problem. And I won't even talk at all about where it can and can't be used. In my lecture, if you started reading through my work, I talk about permutations real briefly, and I say that you can use a formula to do counting principle problems, but we're not going to do that because I don't think it adds anything to your ability to solve the problem. I think it just really confuses more so than anything. So for now, I'm going to skip, and get into the, I'll get into the homework. And then, we'll get to a specialized problem at the very end of the section. So let me jump into the homework real quickly. And then after I get a chunk of the way through the homework, we're going to run into a special kind of problem. I'll talk about it when it makes sense to talk about, but I'm skipping a bunch of the stuff that I have typed up. I'll come back to it, but for right now, let's just start knocking out some of these counting principle problems. So let me just deal with my problem 2 while you do with your problem 1. For what it's worth, the answer I have down for your problem 1 is 56. So my problem 2, a club consists of 10 members. How many different arrangements or how many different ways can they elect a president, a vice president, and a secretary? So in this particular problem, I'm doing 3 experiments. I'm picking a president from the 10 people in the club. I'm picking a vice president, and I'm picking a secretary. So the 3 experiments that I'm going to do here is I'm going to take those 10 members and we're going to give one person the job of president, one vice president, and one secretary. How many ways can they do this? Well, I know for certain there's going to be 10 people to choose from for the president. It doesn't say it, but I think it implies it, that the president also can't be the vice president and the secretary. Once you're the president, you're not going to get another job. So I'm going to increment down. The club had 10 members. One of them's the president. I'm not going to let the president be the vice president, so there's going to be 9 people for the vice president job. And I'm assuming the secretary is not going to come from the president or the vice president, so I'm going to increment down again and get 8 people to choose from for the secretary. I believe how many different arrangements or how many different ways can from this 10-person club, how many different president, vice president, secretary combinations are there? There's 720 of them. For your problem 1, The daily double at most racetracks consists of selecting the winning horse in both the first and the second race. If the first race has 7 entries, the second has 8 entries. How many daily double tickets must you purchase to guarantee to win? So what you have to do is you have to win the first race and you have to win the second race to win the daily double. So your experiments are buying a winning ticket for the first race and a winning ticket for the second race. In order to be guaranteed that I win the first race, I can buy a ticket with one ticket for each of the 7 horses. In order to be guaranteed to win the second race, I can buy 1 ticket with each of the 8 horses, naming them the winner in the second race. If you multiply that 7 times 8, you get the 56 different ways, that 56 different tickets you must have in order to guarantee winning the daily double. Like you pick horse 3 in the first race and horse 5 in the second race, or horse 2 in the first race and horse 1 in the second race. There's going to be 56 different tickets you'd have to buy to guarantee yourself to win. So our problems 3 and 4 are similar, but they're different. There's one word in mine that's not in yours that's going to make it different. So let me just work through 3 with you and make sure we can do this. So I'm going to skip number 4. You're more than welcome to try 3 without me. If you try it and get 15,625, then you did beautifully. So 3 says a lot combination consists of 3 numbers, I'm assuming natural numbers, whole numbers actually, between 0 and 24 inclusive. How many combinations are possible? So my experiment here is picking 3 numbers, 1 for the first number in the combination, and then the second experiment will be picking the second number of the combination, and then the third experiment will be picking the third number of the combination. This is tricky. For the first number, there's the numbers 1 through 24 plus 0, so there's 25 numbers that I could choose from for the first number in the combination. Because it says assume repetition is allowed, that means like if my first number is 7, that my combination could be 777, that I'm allowed to use a number multiple times. So for this case, because repetition is allowed, I'm not going to increment down, and I'm going to keep my numbers at 25. There's going to be 25 choices for each of the first, second, and third numbers for my combination. And that's the 15,625 I wrote for an answer. If I was doing my problem 4, basically says the same thing, except it says I'm not allowed to use a number more than once. If I was doing number 4, I would have the same setup. I'm picking 3 numbers for a combination. There's going to be a first number, a second number, and a third number. There's going to be 25 numbers to choose from for the first number, but mine says repetition isn't allowed, so if I pick the number 7 for the first, I can't pick it for the second. And if I say I pick 7 and 8 for the first 2, I can't pick those for the second. I would have to increment down, and whatever that would multiply out to would be my answer for problem 4. So our problem 5s are essentially the same problem, except the very end. So both of us are trying to figure out how many Social Security numbers are possible. A Social Security number consists of 9 digits. How many different Social Security numbers are possible if repetition is not permitted? In mine, a Social Security number consists of 9 digits. How many Social Security numbers are possible if repetition is permitted? So for me and for you to get started, our 9 experiments are picking each of the 9 digits in a Social Security number. Running out of room. For both of us, there's going to be 10 digits to choose from for the first digit. Any of the numbers between 1 and 9, adding in the 0 to get all 10. For me, my repetition of digits is permitted, so if I pick a number, I'm allowed to keep using it, so I could have the 111191 Social Security number. So for my problem, I'm going to put a 10 in each of the spots, and when I multiply those out, I'm going to get a 1 followed by 9 zeros. When you go to do your number 5, because it says repetition of numbers isn't permitted, that's supposed to tell you what to do in terms of getting to that answer. And the answer I have written down on my answer key is 3,628,800. Your starting set of dashes is going to be the same, but it's not going to end the same way because you're going to increment down because you're not allowed to repeat numbers. So for 7 and 8, I don't know if you can do 7 without me, but I get an answer of 6 for number 7. For number 8, Anthony has 6 dress shirts and 4 ties. How many shirt tie outfits can he make? So Anthony's to experiment in number 8 is his first experiment is to pick a shirt. His second experiment is to pick a tie. My brother's name is Anthony. I believe he has 1 tie and probably 1 dress shirt, so this wouldn't be him. Anyways, how many ways are there to pick a shirt? Well, he's got 6 shirts to pick from. How many ways are there to pick a tie? He has 4 ties to pick from, assuming they all can match together. I guess my brother wouldn't care anyways. My answer is going to be 24. You're going to do something very similar when you go to set your problem 7 up. Talks about a class ring having 3 stone options and 2 metal options. So your experiment 1 is going to be to pick a stone. Your experiment 2 is going to be to pick a metal. You're going to put numbers above and multiply them out, and that should be 6. So your problem 9, if you want to give it a go, I came out with 12 for an answer. My problem 10, a batting order in a baseball game must be created from the 9 starters on a baseball team. This is assuming the pitcher is hitting. How many batting orders are possible? So for me, and for batting orders, there's usually 9 players that play on a baseball team. And we're going to bat the players from 1st through 9th. Start running out of room when I start doing the THs at the end. And this doesn't say anything about with or without repetition, but I know that if a person bats first, they can't also bat second, they can't also bat 8. They only bat 1 of the 9 spots. So this is like a without repetition problem. Once a person has their spot, they can't go into any of the further spots. And so the numbers I'm going to plug in are 9 through 1. And I'm just going to multiply those together. So 9 times 8 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 equals. There are 362,880 batting orders of 1 through 9 if there aren't any restrictions. Your problem 11 is a pretty classic problem. A batting order must be created from the 9 starters on a baseball team. How many batting orders are possible if the pitcher must bat last? So again, I'm going to skip 12 and do number 11. So we're going to bat all the way from 1st through 9th. We have 9 experiments here, picking the 1st through 9th hitters. And on yours, it says the pitcher must hit last. So there's going to be 1 choice for the last 9th spot, the pitcher. When I go to sit the rest of them, the pitcher's batting. Now I have the 8 position players that can bat 1st through 9th. So there's not going to be 9 people to choose from for the first because the team has 9 starters. I've placed the pitcher, so I've placed one of them. There's going to be 8 remaining players that could be first, and then I'm going to increment down by 1 each time because the pitcher can't hit anymore and the batter that's hitting first can't hit again. So I'm just going to increment down. And assuming I've not made any sort of horrible errors. I think this comes out to 40,320 different batting orders that are possible. Let's work on 13 together, and then we'll worry about 15 and 16 on the next page. So, a batting order must be created from the 9 starters on a baseball team. Again, I'm going to go 1 first, second, third, make these too big at the beginning, fourth, fifth, sixth, seventh, eighth, and ninth. Fifth, sixth, seventh, eighth, and ninth. So there's the 9 experiments, placing the 9 hitters. How many batting orders are possible if the first 4 batters are already signed? That means I don't know who's batting first, but their numbers 1 through 4 are fixed. I've got my 4 best hitters. You're my best leadoff hitter. You're my best second hitter. You're my best third. You're my best fourth hitter. If you watch the Diamondbacks, I mean, pretty consistently, the first 4 hitters won't change that much. If certain 4 guys are playing, they're going to hit 1 through 4. And you might see a little shuffling in the 5 through 9. So the team our A baseball team has 9 hitters. And I've placed 1, 2, 3, 4 of them in the first 4. So for the 5th hitter, there's only going to be 5 batters left to choose from. Once I pick the 5th hitter, now there's only going to be 4, and then 3, and then 2, and then 1. If I multiply those out, I think you come out to 120 for the answer to problem 13. '15 and '16 start talking about multiple choice tests. A multiple choice, I'll do 16, you can do 15. A multiple choice test has 5 questions. Each question has 4 choices, maybe A, B, C, and D. How many ways are there to answer the question if you know the answer to the first 2 questions? So let me do this. So there's question 1 I need to make an answer to. Question 2 I need to make an answer to. And all the way through question 5. So there's 5 questions on this multiple choice test that I need to answer. And I know that I know the answer to the first 2 questions. So there's only one choice that I'm going to choose for the first one. It's the right choice. There's only one choice for the second question that I'm going to pick. I'm going to know those answers. But for the remaining questions, questions 3, 4, and 5, there's going to be the choices. There's going to be 4 choices. And I'm assuming I'm completely clueless. And so I have no idea which of the choices is possible. So I'm just going to make a guess. For question 3, there's 4 letters that I might guess from. And there isn't anything restricting me from guessing AAA. As a matter of fact, on multiple choice tests, that's a common strategy. A student will guess C for every problem they don't know with the hopes that there's more C's than anything else, and they start getting, some more answers correct than if they started changing the letter every time they guessed. So for each one of these, I'm going to put a 4 down, because there's going to be 4 that I could guess from. And that should be 64. And your question 15 should be remarkably similar. And for your answer for problem 15, I get 256. All right. So this is kind of like our combination or password problem. An identification code consists of 2 letters followed by 4 digits. How many codes are possible if... Let's just do your 17 right now, because it's a little bit more something like I'd put on a test. So identification code has 2 letters followed by 4 numbers. So if repetition is permitted, there's 26 letters and there's 10 digits. If repetition is permitted, for each of the letters, I'm going to have 26 letters to choose from because I'm allowed to double up the letters. And for each of the numbers, I'm going to have 10 to choose from because I'm allowed to double up the numbers or quadruple up the numbers even. If I multiply these out, I get that 6,760,000 that I got earlier in this video. Let's work through 19 together. You can pause the video and do 19. If I have the right answer written down, I believe the answer is 6,500,000. So again, I'm finding out how many of these codes are possible, and these codes have 2 letters followed by 4 numbers. Notice I'm scrubbing using the word experiment because generally we don't start saying experiment every time. It says repetition of numbers is permitted. So for each of the digits, I'm allowed to use all 10 numbers from 0 through 9. But repetition of letters is not permitted. There's 26 letters to choose from for the first letter. I'm not allowed to repeat that letter, so there's only 25 to choose from for the second letter. Let me just multiply these out real quickly to make sure that number feels good, and that seems so fine. All right, 21 through 24, license plate problems. A license plate consists of 3 digits followed by 2 uppercase letters. So my experiments for these problems are doing the first digit for my license plate, the second digit for my license plate, the third digit for my license plate, and then the first uppercase letter and the second uppercase letter. For your problem 21, I get 468,000 for how many license plates are possible. My problem 22 says repetition of numbers and letters is permitted. So for the numbers, there's going to be 10 digits for each. And then for the letters, there's going to be 26 for each. That's going to be 10 times 10 times 10 times 26 times 26 times 26, and I get 676,000 possible. Hopefully, without me doing 21 for you, you're able to do it. And this will be the last problem for this part of the video, and then we'll do a part 2 with the new concept that I kind of skipped over. So let me just work through your 23 with you. So again, so these license plates are 3 numbers followed by 2 letters. As we go to do problem 23, we need a first number, a second number, a third number, a first uppercase letter, and a second uppercase letter. The first digit can't be a 0 and repetition isn't permitted. So this says the first digit can only be the numbers 1 through 9, and there's going to be 9 choices. It can't be a 0 for whatever reason. So I picked one of these numbers. Let's just pretend I picked the number 1. Since repetition isn't permitted, for my second digit, I have to lose the number that I picked. But the second digit can still be 0. So there's going to be 9 numbers to choose from. The 8 numbers that I didn't pick for the first number plus 0, there's going to be 9 numbers to choose from. For the third number, out of the 10 digits, I will have picked 2 of them. There's going to be 8 digits left. And then for the numbers, I'm going to increment down because repetition isn't allowed. If you multiply those together, assuming I don't have a mistake on my key, I get 421,000.